Good morning, everybody. So we're going to start back up here in chapter 6 this morning. Last time we were looking at this particular problem here, where we were looking at what wavelengths of light are capable of breaking a bond in a molecule of molecular oxygen, O2. And we're told that oxygen has a bond enthalpy of 495 kJs per mole. So the idea here is that one photon of light, if it hits an O2 molecule and that photon has enough energy, then it can cause that bond to break. We want the photon to have exactly or more energy than that 495 kJs per mole that it takes to break the bond in O2. But we're going to think about the energy of one photon versus the energy it takes to break the bond in one molecule. So the idea here, the photoelectric effect. The photoelectric effect is, basically one photon causes like one event to take place. So one photon being the least amount of light you can have. That one single photon can cause one event to take place, but it just has to carry enough energy to cause that change, like breaking a bond or causing an electron to be ejected from a metal atom. As long as we have enough energy in that single photon, then we can cause that change to take place. And we also had seen from the photoelectric effect that E is equal to h nu, where E is the energy of the photon. So the energy of a photon, E is equal to h nu, just a relationship between Planck's constant, we'll mention what that is numerically in a minute again, times the frequency in inverse seconds, or hc divided by lambda, where c divided by lambda is the frequency. Okay, and so we're looking here for the energy it takes to break the bond in just one single O2 molecule. So the first part, this is what we were working on last time, was the number of joules it would take to break the bond in one O2 molecule. We had taken 495 kJs per mole, just use Avogadro's number to get down to one molecule. We could multiply by one molecule, so the molecule cancels, the mole cancels. If we stopped at this point, this would be the kJs it would take to break one O2's bond. And then we just simply do a conversion over to joules. We do the conversion over to joules because we're imagining the next step we're going to use Planck's constant, which is in units joules times seconds. So the joule is a good unit to be in for the next step. And I think this was like the very last thing we had done on Wednesday was sort of calculating this value or setting up this calculation. So it takes 8.22 times 10 to the minus 19 joules to break one O2's bond. And so that's the amount of energy we want that photon to carry. We want the photon to have at least 8.22 times 10 to the minus 19 joules or more, then we should be able to cause the bond in O2 to break. And so we want our photon energy, where our photon energy, again, just from above, is hc divided by lambda. We want that energy to be greater than or equal to 8.22 times 10 to the minus 19 joules. So like this is the last step of the problem that we need to solve to get the wavelength associated with breaking the bond in O2. So one of the things that we could do either numerically when we try to solve for lambda, like if I cross multiply lambda in this equation, then we end up with lambda should be less than or equal to, since we multiply it over to the other side, and then that would be hc divided by 8.22 times 10 to the minus 19 joules. And we can plug h in, we can plug c in, we should be able to solve for this wavelength in, and we'll talk about the units in a minute. But the key would be that we get this less than or equal sign here, just from the cross multiplication of lambda to the other side of the equation. Now, also we might remember that if you go to a higher wavelength, you go to a lower energy. So if you increase the wavelength, you decrease the energy of the photon. Decreasing the energy of the photon wouldn't carry enough energy to break the bond. But if we instead increase instead of increasing the wavelength, we decrease the wavelength, go to a shorter wavelength, then that's going to increase the energy of the photon, going to a higher energy that should cause that bond to break. So two ways of thinking that we want the wavelength to be some value or lower in order to carry enough energy to break the bond for the event for this problem. And so then to actually plug in our numbers here, it would be 6.626 times 10 to the minus 34 joules times seconds. That's a value that would be on your equation sheet. The speed of light would too. but they're probably numbers that hopefully we have memorized here soon. But 2.998 times 10 to the 8 meters per second. And then we divide by the joules we had before, 8.22 times 10 to the minus 19 joules. So the joule unit cancels, the times seconds and the per second cancels. Like the units on Planck's constant is joules times seconds. It's maybe a silly unit at first when you're looking at joules times seconds, but sometimes we get confused and think it's joules per second, but it's not. It's joules times seconds, which cancels the seconds into the per second from the speed of light units, leaving behind just the unit of length of meters. So if we do this calculation, I get 2.42 times 10 to the minus 1, 2, 3, 4, 5, 6, 7. And then all the choices in the problem were in nanometers, so we just do that conversion to nanometers. So 1 meter is a lot of nanometers, 10 to the plus 9 nanometers. So that's going to be 242 nanometers. So if you think of oxygen, oxygen is going to break bonds. It's going to break its bond if the wavelength of light is less than 242 nanometers. So if you think about sunlight, sunlight has to get through our oxygen atmosphere. So we're probably not going to have 242 nanometer light hit us on Earth, because if we did have that wavelength of lights coming through the atmosphere, oxygen would be absorbing it through breaking its bond. We could talk about ozone a little bit on what wavelengths ozone absorbs. So ozone is actually absorbing wavelengths above this. So most of the ozone layer is filtering out a lot of this light, so O2 doesn't really encounter this wavelength of light too frequently in the atmosphere. But anyways, this is the wavelength of lights. So if we look at the choices, we want to go less than 242, because that would carry the proper amount of energy or greater to break the bond in O2. And so that's just kind of the photoelectric effect in action, is just thinking about the energy it takes to cause an event to take place. Okay, now let's get into a topic that gets us to understand what we can learn about the H atom, and then from the H atom maybe we can learn about some information about bigger elements on the periodic table. And so if we think about taking a light source, you can pass it through maybe like a slit, so we can get a narrow portion of light and pass that light through a prism. And then when you do this, you can see the colors of the rainbow emerge. And so the prism is just separating light on the basis of its different wavelengths. And so a light source that has all the wavelengths of light in it would show this kind of like rainbow. And the reason why you would have this part of the process is just you have a narrow portion of light, so you can nicely separate into a rainbow. If we just removed the slit from the process, then we would have like a broadband rainbow, because it would look like a real rainbow in the sky where it's not real distinct. The rainbow here would look a little bit more distinct just due to taking a narrow portion of light, passing it through the prism. Now, I mention this because if we take a different light source, so imagine instead of taking like a light bulb or something in the room where we have most of the wavelengths of light present, what if we take something like a hydrogen lamp? So if we have a lamp here where the lamp has H2 gas in it, and then the gas is subjected to a high voltage electricity, which causes the bond to break, and then presumably what we're seeing are the emissions of light as those like hot atoms are being created and are coalescing back down towards their ground states. And that's really how most lights, like how a tungsten filament's working, is it's absorbing electricity and it's being excited to high energy states, and those states are returning back down to their ground states, and when they return down, they emit the light. And so it's the emission coming from having some, say, hot state that's created from the electricity, and then we're coalescing back down to some cold state. And if you have a lot of atoms, a lot of permutations, you have a lot of different states. So like for tungsten, you have all different kinds of states, and then you get almost all the wavelengths of light in the visible spectrum as tungsten's returning back down to its like ground state. Now hydrogen's a little bit different because it's a simpler atom, it's the smallest atom. When we do this process of putting the high voltage electricity, creating the lamp, taking a portion of the light, passing it through a prism, we actually only get 4 distinct lines in the visible region of the electromagnetic spectrum. So it might be a little hard to see, but there's one line about here, one here, one here, and then one here. And so the fascination I think this is in the 1800s, was trying to understand, well, why is it that you specifically get these 4 transitions? What's causing these transitions? What can we learn about these transitions that helps us understand more information about the atoms? And so the hydrogen emission spectrum, this is something I think you do next week in lab, tries to look at this like in the laboratory where you can kind of verify and see this same basic experiment being done in the laboratory. And so now the specific transitions of the H atom that were observed, now these aren't worth memorizing, but the specific wavelengths were about 410, 434, 486, and 656 nanometers. So the question is, what causes those specific wavelengths of light? Can we understand like how or where those transitions are coming from? And so Balmer, 1885, he tried to just find a formula that would return those numbers. And he succeeded, so he found a single constant that was later called the Rydberg constant for hydrogen. And so there was one constant for the atom of hydrogen, and then if your N1 was 2, and then N2 was 3, 4, 5, or 6, then that would return the inverse of the wavelengths that were measured in the above experiment almost perfectly. So with this one equation here, we could return those wavelengths. And I don't particularly want to plug the numbers in and prove it at this point, but the idea of this equation was, it was like throwing darts. It was like, can we just come up with an equation that gives us those wavelengths back? And this is the equation that was found to be able to do so. And so now an equation doesn't really tell us anything though. So like we don't learn a whole lot just from the single equation. So later Niels Bohr came along and tried to come up with an actual explanation for this model and a better physical picture of what's going on within the H atom. And so the Bohr model was pieced together where we actually were able to get a picture that we could look at hydrogen atom as having different energy levels. And the lowest possible energy level, so energy is increasing upward on this diagram, the lowest energy state would be n equals 1. When we're in that lowest possible energy state, then the next highest state's 2, then 3, then 4, then 5, etc. on upward. And so we have all these different energy states that are possible for the H atom, but we have a big gap from N1 to 2, smaller gap up to 3, and we're going to smaller and smaller energy levels as we excite the atom. Now, on some level, this might, like, you could imagine, well, why wouldn't it go the other way? Why wouldn't it go small gap, bigger, bigger, bigger? Well, if you're thinking about H going to H+, if we had an ever-increasing amount of energy required to go from N1 to N2 to N3, then we would probably never be able to remove the electron from the H atom. And we know we can. We know H+ exists as an ion. And so the other thing would be that it just will help us get towards an understanding of what our experiment was doing. If you remember the hot versus cold, what the experiment was doing was creating hot atoms from the electricity that was absorbed to break the bond, have these hot atoms, and they're coalescing back downward. So those transitions downward that we were observing was creating molecules in the higher energy states, and they're coalescing, trying to get back down towards n equals 1. And so now, if we go back to the previous experiment, what we were seeing is primarily the 2 as the final state, and then the initial states being, again, 3 to 6. You might wonder, well, why weren't we returning to 1? Well, the issue is, think about how much, if the, say, 3 to 4 transition is this energy here, the 3 to 1 transition is this energy. It's a lot more energy. That just wouldn't be in the visible region. So this would be a UV photon in a different region of the electromagnetic spectrum. So we could see this transition. We would just have to look for it in some other device or some other way to actually look at the ultraviolet spectrum. So when we're using a prism and using our eyes to look for wavelengths of light, we're going to be limited to the visible spectrum. And so anyways, an equation emerged that was the energy as a function of n for the H atom emerged that was negative hc times that same Rydberg constant, which I don't think is numerically a number worth even knowing. It's just a constant that's known for hydrogen, and then z divided by n, where z is the nuclear charge of the atom. So z is equal to 1 for H. And so the combination of H times C times the Rydberg constant leads to this number here, 2.179 times 10 to the minus 18, and the units end up being joules. And so that's joules. So the energy of the hydrogen atom, 2.179 times 10 to the minus 18 joules, and then times 1 divided by the n value squared for the atom. And so the lowest ground state would be n equals 1. So the ground state, the GS, the lowest possible state is n equals 1. N equals 2 would be a higher energy state. N equals 3 even higher. And so this equation here is just establishing the energy as a function of the H atom is just being related to this particular equation. And then that each of these energy levels are then for the electron moving further and further away from the nucleus. So n equals 1 as close as the electron can get to the nucleus in its closest possible orbit, if you will, or spinning around the nucleus. And then n equals 2 is a little further away, n equals 3 even further away. So we're just looking at the atom from n equals 1 to 2 to 3, the electron moving further and further away from the nucleus. And then the atom can change energy, so we can absorb energy and go upwards, and we can emit energy and come downwards. And so maybe we can absorb light to go upward for the H atom, and we can emit light for the atom to come back downward. And so the downward arrows are emission, and then the upward arrows, these would be absorbance events or absorption. So we can absorb a photon, go up, emit a photon, and come down. Or absorb energy, go up, and evolve energy coming downward. Now, it's not very easy for atoms in a high state just to evolve heat, so to heat up some other object. It's much easier for them to give off a photon of light. Okay, so again, this slide's are just looking at the values of the Bohr model. So just showing us that going down is emission of energy, going upwards, absorption of energy. So the atom has to absorb energy to go upward and then emit energy to come downward. And so we could look at the n value. So for when the n value increases, that's increasing energy. When the n value decreases, that's losing energy. That's emission. Okay, so now here we can try to look at this question where it's asking which transition below for an electron in an H atom causes the greatest wavelength of light to be emitted. So we have a couple choices here. So we're choosing between 2 to 3 or 3 to 2, and 3 to 4 or 4 to 3. And so we're just looking at our relative energy differences of 1 to 2 being greater, 2 to 3 being lesser than 1 to 2, and then 3 to 4 being even lower. So the lowest energy transition of the choices is the 3 to 4 and 4 to 3. And so those are going to have a lower energy transition. And so again, energy versus wavelength, if those are the lower energy transitions, those correspond to having the greater wavelength. So the greatest wavelength transition is the lowest energy transition. So it's going to be either the 3 to 4 or the 4 to 3. And then which of those two transitions corresponds to emission? So emission is n equals 4 to n equals 3. So this is emission. That's where we can emit a photon. And if we wanted to go from 3 to 4, if we wanted to go from n equals 3 to 4, we have to absorb energy or absorb a photon. So a photon of the greatest wavelength could be absorbed to go from 3 to 4 or emitted to go from 4 to 3. 3 to 2, this is going to have a greater energy. So the 3 to 2, this would be a lower wavelength. So the lowest wavelength would be the 3 to 2 emission, or the greatest wavelength absorbed would be the 2 to 3. Okay, now again, for overall, the 1 to 2, if we're just looking at a change of n value of 1 to 2 is the greatest overall energy change. If we keep going up, the 4 to 5 is lower, 5 to 6 is lower, and eventually you get up to what you might think of as infinity. As n approaches infinity, that's the electron moving further and further away. Infinity is lost. So at the infinity state, this is H plus the electron removed. So that's the electron being removed from the atom. So this is just ionization once we get supposedly to infinity. So if that electron keeps moving further and further away, eventually it breaks free. And so then what wavelength of light could be emitted by when an electron transitions from 4 to 3 in the H atom? So we go from n equals 4 to n equals 3. what specific wavelength of light could be emitted by this atom. And let's do this in nanometers. That's kind of the value we want to put the answer in. And so the way I would think about this problem is that the H atom is going from n equals 4 to n equals 3. So I can calculate the delta E of the H atom by taking the final state minus the initial state just making sure we are seeing that the final state is the 3. So we're in 4, we're going to 3. And so we can plug in to our equation. And like this equation is given on exams here. And so that's like a given equation. You can double check. The 1 over wavelength and the Rydberg constant for hydrogen, that equation is usually given too. I prefer this equation because to me this is where I can sort of see in action what's going on for the H atom. Because for the H atom, I'm just calculating this change in energy for minus 2.18 times 10 to the minus 18 joules, and then times the 1 over that n value squared, so 1 over 3 squared, and then minus, and then it's negative 2.18 times 10 to the minus 18 joules, times 1 over that n value squared of 4. So I just try to do the negative signs also. Negative 2.18 e minus 18 divided by 9. And then minus negative 2.18 e minus 18 divided by 16. So now my hydrogen atom is losing energy, so this should be negative, and it is. So my H atom has lost energy. It's negative 1.05, we'll call it 1.06 times 10 to the minus 19 joules. So H atom's losing energy. And this becomes like a system surrounding problem. Where does the energy go? It doesn't just disappear, it goes into the photon. So the energy lost by the H atom is gained by the photon. So our photon energy is gaining this energy. So our photon energy is the negative of the energy lost by the H atom. So of course it's just plus 1.06 times 10 to the minus 19 joules. So we can see H atom's losing energy. Where does it go? It goes into the creation of a photon. I like to think of it almost like this. Like if we're picturing a wave, it's like this just creates that wave that emits off of that change. So we have the loss of energy, goes straight into forming that wave, and that wave carries that energy away from the atom. And so the photon energy is plus 1.06 times 10 to the minus 19. Photon energy is hc divided by lambda. Same problem as before, where we're just solving for that lambda. So I can take my lambda, hc divided by that energy. And I'm not even going to, so it's just h is 6.626. Actually, you know what? It's probably worth writing just so we can use this to help us. The more times you write a number, the more times I think you'll remember it. So 6.626 times 10 to the minus 34 joules times seconds times 2.998 times 10 to the 8 meters per second. And then divide by 1.06 times 10 to the minus 19 joules. So I get 1.87 times 10 to the minus 1, 2, 3, 4, 5, 6. multiplying it by 10 to the 9 to go to nanometers. 1870. So now the visible is 400 to 750. This definitely isn't in the visible region. So if you're wondering, like, why was it just the two? It was 3 to 2, 4 to 2, 5 to 2, 6 to 2. Those were the 4 visible peaks that we saw in the visible transition. This one here would be in the infrared. So this is an IR transition. So the next slide kind of summarizes some of the different types of transitions we can see for the H atom. Now the Lyman transitions are the ones that go all the way down to 1. So it's the 2 to 1, 3 to 1, 4 to 1. These are in the UV region, and even in sometimes what we call the vacuum UV region, where the wavelengths are so low they can't even permutate through air because they'd be absorbed by the O2 and N2 molecules. So these are really high energy UV photons, or even deeper than that. The Balmer series, these are our visible photons. If you imagine going beyond 6, if you go 7 to 2, 8 to 2, those start to get into the fringes of the UV region. So you can get into the UV when you get like 7 to 2, 8 to 2. But these are the visible photons primarily within that Balmer series. These are not names I would necessarily memorize, but just to get a sense of the transitions that end in 2 are the ones you can see in the visible region. And Passion series are the ones that go 4 to 3, 5 to 3. These would be in the IR, the infrared region. So you can kind of get a sense of where you're going to find some of these different transitions for the H atom. You can see them all taking place within the emission of hydrogen. You just have to go looking for them in the proper region of the electromagnetic spectrum. And then lastly, if we go from n equals 1, if we take an H atom in its ground state and we take it all the way up to infinity, that's ionization. And so we can actually calculate the ionization energy of hydrogen, because we would be taking the delta E for our final as infinity minus the energy of the 1 state. So as n approaches infinity, as you're dividing by infinity in the equation, so we're taking 1 divided by the n value squared. So this is approaching 0. And so the negative of 2.18 times 10 to the minus 18 joules. So the ionization energy of hydrogen is 2.18 times 10 to the minus 18 joules. So you can sort of get a sense of how much energy it takes to ionize the H atom. It's that energy there. And just to convert that to kJs per mole, all we have to do is multiply that by Avogadro's number. I doubt we would even ask you to do this calculation, but I just want us to see the number, what it corresponds to. It's 1312 kJs per mole. So it takes over 1,000 K. If you think about bond strengths, this is a pretty high energy compared to those bond strengths. So a good amount of energy to ionize the electron off of the H atom. And the one thing that's interesting is this is like the exact number. Like this is the true number for the H atom, what its ionization energy corresponds to. So from a relatively simple equation in relationship to the H atom, just as a function of n, we can understand properties like ionization energy of H. We'll talk more about ionization energies in our next chapter. Okay, so for hydrogen, we can have an equation. We can have an idea of orbit size as a function of n. It's very clean. You can have experimental data that is backed up perfectly with the equations. For anything with 2 electrons or more, this does not work. And so that's like kind of one of the interesting conclusions is we can do this for H. We can learn about energy levels. So we're learning about one of the quantum numbers that electrons can have in an atom, this n value. We're going to see that relates to the orbit size that the electron's spinning around its nucleus. But then for other atoms, we're going to have a more general way of thinking about where its electrons are. That's where electron configurations will come into play, as opposed to discrete like energy transitions like we can see for the H atom. So we can do this for H, but we can't do this for any other elements in the same way. So now, I had mentioned there's a French scientist that has a peculiar pronunciation. This is the scientist, so Louis de Broglie, as I guess the French pronunciation. I call this de Broglie because it looks like de Broglie to me. But in 1924, he sort of was thinking that light can have material properties. Well, can material have light properties? So if light can behave like a particle, can a particle behave like a wave? And so what he tried to do was demonstrate that the electron and things small like an electron, that there could be a relationship between their mass and the wavelength of the particle. And so this is the wavelength of a particle, like an electron. So an electron, we can take Planck's constant, divide by the mass of the particle, and then times the velocity of the particle. And you can imagine that there's a couple slides. We're going to look at a baseball versus an electron. So we're going to compare an ordinary sized object that has a relatively high mass, relatively small velocity, and kind of see that its wavelength isn't anything special, nothing to really concern yourself with. But when you get to a particle that's really light and fast moving, when you make the mass of the particle really low and the velocity really high, then the wavelength becomes an important property, and you can think of that particle as having a wave-like behavior with its trajectory, with its motion. And so that's the de Broglie wavelength. And then also Heisenberg, one of the scientists probably made famous by Breaking Bad, because Heisenberg was the main character's moniker. But so Heisenberg showed that there was sort of an inherent impreciseness for the location and the momentum of particles, and it became known as the uncertainty principle. And so the uncertainty principle is that the uncertainty in position, so if we're thinking of x is an electron's being fired across, say, a potential, so we have an electron firing across a potential, the location of the particle is x, and then the uncertainty in where the particle is plus minus delta x. So imagine you have the particle here, but then you have some inherent uncertainty of where the particle is. So you don't exactly know where the particle is, but you have some measure of uncertainty of where the particle is. And so it's that uncertainty that factors into the uncertainty equation. And then you have some measured velocity of the particle at that moment, which also has some inherent impreciseness about it. So you have a delta mv. Now, the mass of the particle is usually a constant. Usually the electron's not changing mass, so a lot of times this can be m delta v. So it's the mass of the particle times the uncertainty and velocity. So it's not the velocity itself, but it's the uncertainty. So like if a particle, for example, has a velocity of 5.0 times 10 to the 6 meters per second, the uncertainty is the plus minus. Like let's say it's 0.1. If it's 5.0 plus or minus 0.1 times 10 to the 6 meters per second, the uncertainty is the 0.1. The uncertainty in velocity would be 0.1 times 10 to the 6 meters per second. So this is the uncertainty in that velocity. You can think of it as like the error in the measurement. So it's how well you can know those particular positions and velocities that have a fundamental relationship to each other. Now, why this is that the uncertainty in x, the position, times m delta v, the mass of the particle, times the uncertainty in the velocity of the particle has to be greater than or equal to Planck's constant divided by 4 pi. This falls out of like graduate level quantum mechanics. So if you want to know where this equation comes from, I highly encourage you to major in chemistry or physics and go to grad school for quantum physics or quantum chemistry, and you'll see where this comes from. So it's quite a complex derivation. But it's also often misused. That I once was in an English class here when I was an undergrad, and we're talking about The Great Gatsby or some book, and somebody said, well, because of the uncertainty principle, we can't know anything. And I was like, I don't think that's what the uncertainty principle is. I don't want to be the scientist in the room, but the uncertainty principle is just talking specifically about the position and the momentum of a particle being simultaneously known. It has nothing to do with knowing something, so two totally different ideas. But so this is just going to lead us into a problem of the electron being a particle that we can't quite ever know where it is with certainty. And so we're going to start to think about probability distributions, or like orbitals of the probability of where we expect to find an electron, as opposed to a baseball where you can see a baseball going from one spot to another. I like to think of the uncertainty principles like if you remember or can think of like a hockey puck, maybe in a video game. If you play a video game and a hockey puck has like a tail on it, that's kind of like the electron moving, where electron moves is like a cloud, where the cloud is describing your certainty of where the particle is, or your inherent uncertainty in where it is, and having an unclear picture of what its velocity is. So let's take a look at these equations in action. These aren't exactly the most important calculations to learn how to do. These are more just to kind of show you what it kind of looks like for a big particle versus small particle. So I think it's just easier to see these calculations kind of given to us here. And so we're just comparing this de Broglie wavelength, the wavelength of matter for the baseball at 95 miles an hour, which is 43 meters per second. So our mass of our baseball is 0.145 kilograms versus an electron, 9.109 times 10 to the minus 31 kilograms at a velocity of 3.0 times 10 to the 6. So this is like an ordinary velocity for an electron. So this isn't like an extraordinarily fast electron. This is just how fast electrons move. And so let's look at the baseball first. I'll learn how to move these things. So again, we're looking at h divided by mv. And so we're taking Planck's constant, divide by the mass, divide by the velocity. Now, you might wonder why use the meters per second or the miles per hour. You can probably appreciate this little detail here, that if you're using values in their SI units, like joule is the SI unit of energy, then you should probably plug mass in SI units. And so we want mass to be in kilograms, which is the SI unit of mass, and we want the velocity to be meters per second. Now we can break down the unit of the joule. We talked about this in chapter 1, that 1 joule is 1 kilogram meter squared per second squared. So that's kind of how we get back into seeing where the units of kilograms and meters and seconds come into play with the joule. So we just convert the joule over to kilogram meter squared per second squared. So this is just the joule. And joules times seconds still. So kilograms meters squared per second squared. And then our kilogram cancels. One of our meters cancels. And then divide by seconds here cancels with this one here. So we have per second in the denominator. That would flip up to the numerator to be, if we're looking carefully at the seconds and how these cancel, we get rid of this here to become seconds squared, and then seconds squared cancels with the per second squared. And so that gives us a unit of just length out. So only one of the meters canceled. We had meters squared, and only one of them canceled. So this leaves behind our value as 1.06 times 10 to the minus 34 meters. Okay, let's think about what this is trying to tell us. It's telling us baseball is traveling from pitcher's hand to home plate, and it has this incredibly short wavelength. That's just a straight line, right? This isn't like a real wavelength. This is just the definition of what it would mean to be traveling in a straight line. Or like, we're just getting, that's just what it means for the particle to really be traveling on a straight line trajectory. Now, the baseball could arc. That's a different wavelength. That's because of gravity. So that's a different wavelength. That's not the wavelength we're talking about. We're talking about the natural wavelength of the baseball. It has no natural wavelength, is what we're concluding from this equation. But now let's compare that with the electron. Again, we're thinking of electron maybe coming across a potential. So we have the same basic equation of h divided by mv. So I've gone ahead with h kilogram meter squared per second squared times seconds for joules times seconds. And then, of course, sticking with the mass in kilograms and the velocity in meters per second allows us to calculate that the wavelength for the H atom is now on the size of the atom. So like if you think about the wavelength coming out for the electron to be 2.4 times 10 to the minus 10 meters, that length is about if you think of the diameter of most atoms is about 1/2 to 1 angstrom. This is about the trajectory that an electron is spinning around a nucleus. And so as the electron spinning around a nuclei, it's traveling with some wave-like behavior would be the conclusion. And so this is a wavelength that's on the size of the trajectory of the electron, so it's an important value to consider for something like an electron. And then for, what about the uncertainty principle though? When we're doing the uncertainty principle calculation, where we want to calculate the uncertainty in the position of the baseball, traveling at the same speed, but here we want to throw in the idea that it's not the speed itself, it's the uncertainty in the velocity. It's like how well do we know it's 43 meters per second is really what comes into play. And so let's say our uncertainty is 1 meter per second, and so that's probably like 95 plus or minus 2 miles per hour. And then we have an electron traveling 3.0 plus or minus 0.1 times 10 to the 6 meters per second. So now for the uncertainty principle, it's the plus minus 1, that this is the uncertainty for the baseball, or it's the 0.1 times 10 to the 6 meters per second that factor into these equations is the uncertainty in those values, and not the velocities themselves. So when we plug in, and we might do a little rearranging too, the delta x, we're going to want to divide our equation here by m delta v. So the mass is a constant, the mass isn't changing, it's the uncertainty. So we're going to divide h by 4 pi mass times volume, and our uncertainty in the position has to be at least this quantity or greater. And so we're plugging in h. So again, h is just almost better thought in these problems as going kilograms meters squared per second squared for joule times seconds, and then divide by 4 pi mass of the electron. And note that I'm plugging in 1 meter per second here, not 43. So I'm plugging in the uncertainty. And so then we work this out here, and we get 3.6 times 10 to the minus 34 meters. And so my uncertainty in the position of the baseball is effectively, like, I have perfect idea of where the particle is. Like, there's almost no limit on where the baseball is. And of course, we see a baseball being thrown, we can see it the whole way there. It doesn't ever become like a cloud on the way to the catcher's mitt. And that's because the baseball's big enough and the velocity is low enough to not come into play. But now for the, let's compare that for the electron. So if we do this for the electron, so for the electron, we have our uncertainty in the position is Planck's constant, divided by 4 pi, mass of the electron much lower, and the velocity much higher. And so that works out to be 5.8 times 10 to the minus 10 meters. And again, I glossed over the conversion perhaps up here, that 1 angstrom is 10 to the minus 10 meters. So 2.4 times 10 to the minus 10 is just 2.4 angstrom, and then 5.8 times 10 to the minus 10, rounding to 1 sig big, just 6 angstrom. So in other words, for the electron, which has a wavelength of about 2.4 angstrom at this velocity, and then our uncertainty in its location is like 2 to 3 times its wavelength. You know, we have almost no idea where this electron is the moment we know that velocity. So it gets us into thinking of like a cloud distribution, or an orbital picture would be better for electrons, to describe that they're now waves or they exhibit a wave-like behavior, but then in a fast enough behavior where the best we're going to do is a cloud of where we expect to find the electron, as opposed to thinking of it as a discrete particle. And so those are the main conclusions of these equations. They're just starting to think of electrons and multi-electron atoms are going to be better thought of as being in orbitals. Okay, so now the concept of orbitals and quantum mechanics, like if you were to take like a grad quantum class, you almost start with this of trying to derive why it is that like a string connected to 2 lines has to have these integral values of either having n equals 1 for just like 1 wavelength connecting, or having 1 node, or having 2 nodes. And you can only get replicating waves if you have a whole number for these nodes. If you had anything other than this, the string just wouldn't propagate across the 2 potentials, if you will. And so you can think of standing waves as leading to these whole number values. And so, because one thing you might be wondering for like the H atom, why do we have n1 to n2 and not n1 to infinite values between 1 and 2? And the answer is, well, if this thing's a particle and it has to spin and it has to act like a wave, then we're going to be subject to these like pinch harmonics that you think of as just from a simple string. And that the particle traveling in a circle is going to have the same problem. In order to replicate that motion in that wave and to have these nodes, if you will, then we're going to have the like sort of quantized energy levels. And we can't just have any energy level for that electron spinning around the atom. And so this is just another picture on why we get quantum numbers or different whole number values for our transitions for our H atom. Now, I often think that the existence of quantized matter. Like the fact that energy levels have some inherent energy that has to be overcome to get to the next higher energy state is good, because if it just took us, if any tiny amount of energy got you into a higher energy state, then I don't know how anything like not particularly stable could exist. Like if you think of life, we're in states that are of matter that aren't exactly the most stable. Like CO2 and water is the most stable. Organizing DNA and sugars and all those things, not very stable, but stable enough because of quantum mechanics, I think. Stable enough because we can have these states that have an inherent lifetime, because it takes so much energy to get up to the transition level to get them to some other state. So quantized energy levels are useful. They allow states that maybe aren't necessarily the most stable to exist for some period of time before they transition over some barrier to some other state that's overall lower in energy. Okay, so Schrodinger developed an equation that, again, if you want to be a physics or chemistry major and go into the quantum side, you'll learn a lot about the Schrodinger equation, H psi is equal to E psi. It's just getting to the idea of a wave function, or a wave function squared is actually what's being shown in this picture, as the observable of where the electron density is in a molecule. The Schrodinger equation is kind of relating to the wave function, or where the electrons are surrounding an atom. And if you operate on the wave function with something called the Hamiltonian operator, you return the energy of the wave function. But it just gets us into thinking of the wave function squared as some probability distribution. And so the wave function squared is a probability distribution where the higher shading is where the higher probability is for finding an electron. And so this might be like a 1s orbital of H being shown here, where the highest probability is going to be pretty close to the nucleus of that atom. So now we don't talk any more about Schrodinger than on this slide here. So if you see this equation, we'll learn more about it. It'll be advanced physics or physical history classes. So now where we get into talking about quantum mechanics in this class is to talk about the quantum numbers that describe the location or the types of orbitals being used by electrons and multi-electron atoms. And so before we get into really probably a topic most of you guys remember, because again, we started this off with like carbon, 1s2, 2s2, 2p2. A lot of you guys might remember that. But to kind of remember, or to get a sense of why it goes from 1s to 2s and then 2p, understanding these quantum numbers hopefully will help us get there. So the principal quantum number n relates to the size of an orbital. As the n value increases, the orbital becomes bigger. This was the same value from the Bohr model. So n1 to n2 to n3 means that the radius of that orbital is increasing, the size is increasing with n. Now we have three other quantum numbers. One of them is the angular momentum quantum number, takes the symbol L. The L value can be 0, 1, 2 integral values, but only as high as n minus 1. Okay, so one of the parts that as we start introducing the quantum numbers, we also want to start thinking about the range of values. The range of values has a little bit to do with maybe the atom we're looking at if we're thinking about where the electrons are in the ground state of the atom. Or we can just start to think of, well, if n is 1, then what could L be equal to? So the lowest L can be is 0, and then the highest it can be is the n value minus 1. So and this gets a little bit confusing because we're trying to like get a sense of what these numbers are, what they can be, and at the same time we're trying to think of what the range of the values can be and how they all interrelate to each other. And these are all relating to an electron and a multi-electron atom. So just imagine you have an electron, and if that electron's n value is 1, then the only possible L value it can have is 0. And because the next value 1 is higher than n minus 1. So the highest we can go is n minus 1. The n value is 1, so the highest we can go is 0. And so then the L is telling you the shape of the orbital or the type of orbital. So the L value is corresponding where the L0 is an S shape, L1 is a P shape, L2 is a D shape, and L3 is a F-shaped orbital. And we'll show you some of those shapes as we go along. This is the worst written F ever. So that's an F-shaped orbital. And there's other slides that get at the S versus P versus D versus F shapes, but those are coming from the L value. And so this here would be referring to the 1s orbital. So N1, L0 is just a 1s orbital. So these two orbitals together define, so the n value And the L value is telling you, well, what is the orbital, so it's telling you something about the orbital. There's another word, it's telling you the subshell. That's the word I was looking for. So the N value and the L value together tell you the subshell. So we have the 2s subshell. If you had a different N value, if we say we had a different electron where the N was 2, well, the L value for that electron could then be 0 or 1. And then the 0-2 combination, that would be the 2s. And then the 1-2 combination, so the N2L1, that would be the 2p subshell. So we have the 2s subshell and then the 2p subshell. We'll look at more ranges as we go along, but let's look at the next quantum number. The magnetic quantum number takes the value m sub L, and this is telling us how many projections or orientations there are possible for the orbital. Now the range of m sub L goes from the minus L value through 0 to the plus L value, all whole numbers in between. And so now if we look at our n equals 1, L equals 0, what's the range of m sub L values? Plus L to minus L through 0. So the only m sub L possible for that is 0. So there's just one 1s orbital. So the 1s subshell, there's just one of them. There's only one orbital that's in that subshell. But if we then look at the n equals 2 combinations, so when the 2s orbital, the L was 0, the only m sub L is 0. So again, there's just one 2s orbital. But then when we look at the 2p, the L is 1, so the m sub L is the minus L, 0, plus L, all integers between. So minus 1, 0, 1. That's 3. So there's 3 2p orbitals. So we go from 1, 1s, 1, 2s to 3 2p's. If we look at our periodic table, we get 2 elements, hydrogen, helium. We get another 2 elements, lithium, beryllium. Then we get 6 elements. You can kind of start to see these orbitals in process. The final quantum number is telling us you're getting 2 electrons per orbital. The magnetic spin can be spin up or spin down, plus a half, minus a half. The plus and minus versus, like when we start thinking of like a 1s orbital, and we start thinking spin up, spin down, the spin up, the plus half is just with the field, minus a half is against the applied field. Don't, like writing things up or down get a little confusing sometimes. Like for H, it has 1 electron. We write it, usually spin up by default, but usually we're writing hydrogen just 1 electron, so we write it as like a 1s1, 1 electron spin up. Helium, 1s2, 2 electrons, 1 up, 1 down. Pauli exclusion principle is telling us that each electron in an atom has to have a unique set of these quantum numbers. So every electron has to have its own like location. Electrons can't be over top of each other. So the Pauli exclusion principle says each electron in an atom must have a unique location, hence a unique set of these 4 quantum numbers. Okay, so this slide's getting a little convoluted. We're also starting to run out of time, but let's just end with this for hydrogen versus helium. So hydrogen, we can have n equals 1, L equals 0, m sub L equals 0. M sub S is either plus a half or minus 1/2. Like we don't know. It's just one of those 2 spins. It's like either the plus half or either the minus half. And it doesn't even matter. It's just if you have a magnetic field applied, the plus aligns with it, the minus aligns against it. Helium, same quantum numbers, and it's the plus and the minus a half. So just the only difference for helium is the m sub S includes the plus half and the minus half. All right, so we'll piece together more about quantum numbers and configurations when we get into class on Monday. So have a great weekend. Go Buckeyes. Back to football. My week be gone.